So all these short channel effects are essentially, bad for your device or your circuit performance. So a good analogy to understand these short channel effects, especially which people from mechanical engineering kind of background might find very intuitive to understand, is that you have these two beakers. Let me denote one as source and another as a drain, and there's this nozzle, and the electrons which are the source beaker is full of electrons who want to flow into this drain beaker because it's at a lower height, or in electrical sense it's at a lower potential. So these electrons want to flow from, there's a potential difference, and these electrons want to flow from here to here. And then your gate electrode is essentially like a nozzle which is controlling this flow of electrons from the source to the drain. So this gate electrode is very effective in controlling this flow if you have a long channel device. But if you bring these two beakers close to each other, you have this short channel device where you have your source and drain beakers very close to each other, and this one single nozzle is not sufficient to control the flow of electrons. So there'll be leakage of electrons from the source to drain, and this one nozzle is not sufficient to control this flow. So using this analogy, we can simply think about now what do we do to improve this, cut off this leakage, or improve the gate control. So using this analogy, it's very simple to think that what we need to do is essentially put another nozzle here. So maybe use two nozzle, or use a double gate device, or maybe put another nozzle on the side over here, or use a triple gate or a tri-gate device, or maybe put a nozzle all around it, and use a gate all around device. And that's that's a very good analogy to understand why there is a need for these devices, or these devices with improved electrostatics to improve the short channel effects. So let me try to use this analogy of this beaker and this nozzle and the pipe to illustrate to you devices with improving electrostatic control. So plotted on this cartoon essentially are devices with increasing electrostatic control of the gate. So from each arrow, the next device has a better electrostatics or a better gate control on the flow of the carriers. So using that analogy of our nozzle and the pipes, in a planar device, essentially you have this one nozzle which is controlling all the flow of these electrons from your source to the drain. So the very first, the simplest way to improve the gate control is essentially to thin down our pipe, or decrease your channel length, so that your gate can now more effectively control this flow of electrons from your source to the drain if you have only a limited volume of your channel material. So that is shown here. If what you do is essentially you have a very thin channel, you have a very thin silicon channel, which is now sitting on top of an oxide material. So you have a silicon on oxide, or a SOI wafer, and this is the most simplest way to improve your gate control. You can further improve it by using another gate here. So you can have this thin channel, and you can use this top gate, and you can also use either put another separate gate, or use this substrate below as a gate, and you can have a double gate device. Another way to make this double gate device is essentially to flip it over. So right now it's in one plane, but you can rotate it by 90 degree. So you have, instead of putting two gates around this thin channel, you put through the thin channel. So this is your channel material now, and now you have this one gate here and one gate here, so you have two gates on the side, and this is what is known as a FinFET device. And you can, so the only difference between a fin gate and a tri-gate device is in a FinFET device you have two effective gates. You have a thick oxide here, so essentially if this is your channel material, so this is your fin. If you, in a FinFET device, essentially you have one gate here, you have one gate here, and you have another material, say you have a thick oxide, or you have a nitride here, so you don't really use the top surface for your transport. So that's your FinFET device. On a tri-gate device you also use the top electrode, so you have your fin, and you essentially put a uniform gate oxide and you use all the three surfaces for your transport. So that's the only difference between a FinFET and a tri-gate device, that in a tri-gate device you use the top surface as well, and in a FinFET device you essentially only use your side walls. So having this gate on the three sides further improves your electrostatic control. You can even go one step further by not only including it on the side, but having this gate protrude a little bit, going a little bit below your fin. So that is, it's essentially, if you have a fin, your gate is essentially wrapping it around in a pie shape around your fin. So that's your pie gate device over here. You can go even further and improve, have it in a shape like this, where essentially it looks like an omega shaped device. And the ultimate electrostatic is if you have your gate wrapping all around, and that's your gate all around device. So expanding on this a little bit further, I'm borrowing these view graphs from a press release from Intel on their 22 nanometer technology, and what it shows is essentially the two most common methods to improving your gate control or improving the electrostatics. So one is this fully depleted SOI device, where essentially you have a very thin channel on a SOI substrate, and this gate is able to fully deplete or fully control this channel by depleting the whole width of this channel, by depleting the whole thickness of this channel material. And this is the other variation, where you have a tri-gate device, where you have a channel protruding out in the shape of a fin, and you have your gate electrode wrapping it around on all three sides. And this is the same 3D view of this device. And so Intel, for they announced that they'll be using this tri-gate device for their 22 nanometer technology, and other companies have publicly announced, like TSMC has publicly announced, that they will be also using this tri-gate or FinFET devices for their 14 nanometer technology. And but there's some IDF manufacturers who are still exploring a fully depleted SOI. So this is still an option on the table. So what both of these do, as we discussed earlier, is essentially they help you improve, again in a planar device. Now, instead of having an ideal subthreshold slope, you had a poor subthreshold slope, a subthreshold slope of 120 millivolt per decade for a small channel device. And this tri-gate device essentially brings you back to that original subthreshold slope. So it improves your subthreshold slope. Also, it decreases your off current. So you improve your leakage performance. So you reduce your off current, which is very important for reducing the standby power and so on. And so that's this is an experimental data point released by Intel in their press room, where they're showing the advantage of going from a planar device to a device with improved electrostatics.